Hello, everyone, and welcome. Thank you for joining us today. My name is Aaron Brister, and I'm a Technology Manager and Commercialization Specialist at NASA Glenn Research Center, or NASA GRC. Today, the NASA Technology Transfer Program is pleased to present a webinar on GRC's luminescence-based temperature mapping sensing systems. Next slide, please. Our presenter today is Dr. Jeffrey Eldridge. Dr. Eldridge received his undergraduate degree in physics from the University of Chicago. He later earned a PhD in physics from Case Western Reserve University. He spent 3 years as a research associate at the National Research Council of Canada, where he researched thermal oxidation of aluminum and aluminum-containing alloys. For his 20-year career with NASA, Dr. Eldridge developed spectroscopy-based monitoring tools for both space and turbine engines. This included developing tests to evaluate interfacial strength in fiber-reinforced composites, Raman-based strain measurements for pressure vessels used on the space shuttle, and luminescence in turbine engines. In addition, he has over 70 publications to his name. Following Dr. Eldridge's presentation, I will be giving a short discussion on how NASA's Technology Transfer Program works. But before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box in the lower right corner of your screen. We will answer your questions during a Q&A session at the end. And now, Dr. Eldridge.
Thank you, Aaron. I'm Jeff Eldridge, and it's a pleasure to be speaking to the audience out there about this technology and hopefully generating some interest, possibly of some people adapting this. Let me start out at a very basic level, asking the basic question: why is temperature measurement important? In particular for the industrial and technology community, focusing on high temperature applications. And here are a few examples, starting with the steel and ceramics industry. It's certainly important when you're processing a material. For many of the stages, you want to have the material at just the right temperature for just the right amount, length of time. And that has to be reproducible. So maintaining the correct temperature is essential for producing high quality products. In the nuclear industry, where we know there are components such as control rods that we need to keep under a maximum temperature. And this is important for the safety of the surrounding community. Now let's turn to an interest of NASA. Remember, the first A in NASA is for aeronautics. We're interested in turbine engines, and the temperatures are obtaining temperatures are important, not only for the hot combustion gas, but the components in the turbine engine. And all these temperatures and knowing the temperature and getting at the right temperature are important for safety in flight, fuel efficiency, and emissions. Now, here's a little bit of background on temperature measurements. By far, most temperature measurements are made with a contact sensor, such as a thermocouple or resistance temperature detector, RTD. But in certain applications, especially in industry and technology, this has some significant limitations. First of all, you have to attach your discrete sensor to what you're trying to measure the temperature of. These require wired connections for the most part. And you can imagine this can be difficult to implement for moving parts. These measurements are intrusive. For example, you can use a thermocouple, insert it into an automobile engine, measure the temperature of the combustion inside there. But it's pretty intrusive to do that, and I can't imagine that someone would do this with the engine in their car. Electrical-based measurements are also susceptible to RF interference. Therefore, there's been a big driver for doing remote, non-intrusive, non-contact temperature measurements. And the workhorse for this by far has been the pyrometer or a thermal imaging camera, which is essentially an imaging pyrometer. Now, a pyrometer works by measuring the brightness of an object, which gets brighter as it gets hotter. And you just need to calibrate that to know, to convert the brightness to temperature. You can imagine have a pyrometer pointed at a turbine blade through an access port to measure the temperature without contact. And you can even measure a temperature as that blade passes through the field of view of that pyrometer. However, there are applications where measurement uncertainties associated with pyrometers will be unacceptable. And these issues are, first of all, to convert your brightness from the thermal radiation to temperature. You have to know how much it's going to radiate at that temperature. For that, you need to know the material's emissivity. You must know that emissivity, and it must be stable over the duration of your measurements. Pyrometers can also be confused by reflected radiation. With your pyrometer, what you're trying to measure is the thermal radiation your object is emitting. But if you have a hot surrounding, your object is also going to be reflecting from the hot surroundings. Your pyrometer doesn't know that that's been added onto your signal. So that you could end up measuring an artificially high temperature. Also, the pyrometer or thermal imaging will not always give you a surface measurement, temperature measurement, depending on the opacity of the material. That's what brings us to the luminescence-based temperature sensing. That's the subject of this presentation. And first of all, it shares the non-contact advantage of pyrometry. However, it overcomes some of the issues associated with measurement uncertainties by a pyrometer. And that's because these measurements don't have the interference from reflected radiation. They're insensitive to surface emissivity, and you can make them intrinsically surface sensitive. Now, the innovation I'll be talking about today is a specific approach to using the luminescence sensing for temperature measurements. And it's based on a breakthrough discovery of exceptional high temperature retention of very bright broadband luminescence by chromium-doped rare earth aluminates that have an orthorhombic perovskite structure, a structure shown here. Now, among the rare earth aluminates doped with chromium, it turns out that it's gadolinium aluminate doped with chromium that gives you the highest temperature capability. We've used this for temperature measurements up to 1300 degrees C. That's 2400 degrees F. Although that gets you to the highest temperature, some of the other aluminates, although they don't get up to that temperature, can have higher emission strength at lower temperature for better signal to noise. For example, chromium-doped yttrium aluminate. So you might want to choose another aluminate if you're not trying to get to such a high temperature. The summary of the benefits of this technology are, first of all, the high intensity of the emission enables a luminescence-based temperature measurements when you have a background of high thermal radiation. And that's because that strong emission will then stand out when you have a strong radiative background. Now, typically, you only get the very bright emission from the transition metal doped phosphors compared to lower emission from the rare earths. And conventionally, the transition metal phosphor luminescence has an upper limit of about 600 C. So getting up to 1300 degrees C is a big step forward. Another advantage is the utilization of this broadband spin allowed emission. And this emission is at a shorter range of shorter wavelengths than is typically used for transition metal dopants. And because you're at shorter wavelengths, you have less thermal radiation background. The high emission intensity also enables the 2D surface temperature mapping, giving you both high temperature and spatial resolution. Now, just for one slide, I want to show you the physics basis for maintaining this ultra bright luminescence to high temperatures in chromium-doped gadolinium aluminate. When we have the chromium in that lattice, we look at two emission bands. I show the three energy levels. Don't worry about what they're named. I could have easily called them level 0, 1, and 2. Now, with your light, either laser or LED, you can excite electrons into this 2E level. And plenty of people do that. This gives you this well-known R-line emission, fairly sharp. And people have used that for temperature indication. In the approach we use, we take advantage of the fact that when a material becomes hot, you can start thermally populating the electrons that were already excited to this level here up to the 4T2 level. And when that relaxes, you get a higher energy, shorter wavelength broadband emission. Now, typically, the 4T2 relaxation would be too short to be useful for temperature indication, but we take advantage of the fact that the 2E level below here in this material acts as a long-lived reservoir. So as you start depleting the 4T2 population, it gets replenished by this reservoir. The two relaxations come to thermal equilibrium, so they end up sharing the same decay time. You can look into the modeling of that and determine the decay time for both emissions. Tau is the decay time, and this shows its dependence on temperature. Now, to have good high temperature measurements, you don't want your decay time to become too short. So for this to remain long, you want your delta E here and delta EQ to be as big as possible. Now, delta E is simply the energy difference between these two excited levels, and the delta EQ is an activation energy for non-radiative decay. Now, if you go over and look at what's called a Tanabe-Sugano diagram, it shows you that as you go to materials with higher and higher crystal fields at the dopant location, this will give you a larger and larger delta E, which is what we're looking for. And that led us to the selection of our chromium-doped gadolinium aluminate and some of the other aluminates, because this material gives you the highest delta E you can really find. Even it's larger than what's seen for ruby, which is already considered to have a high crystal field. Okay, that's some of the physics. Let's go on to some of the data. This shows how the emission spectra change with temperature. At room temperature, in this case around 20 C, you only get that R-line emission that's been used by many others. It's pretty sharp, around 730 nanometers for chrome-doped gadolinium aluminate. Plus, it has a vibrational sideband. As you increase the temperature, though, you populate that higher level and you get emission from it, from the relaxation. That's the broadband here. As you increase the temperature, that becomes more prominent at the expense of a reduced R-line emission. Until when you start getting around 1,000 degrees C, all you see is the broadband, and there's no R-line left. So that's the basis of our approach. Besides the selection of the material, is to use this broadband emission. Now, if your sole object was to maximize the amount of broadband emission to collect, you would collect this entire spectrum. But we decide to collect just on the short wavelength end of that. And that's because of the thermal radiation background. When that's strong, that tends to be strong in the red and in the infrared, and not too much down at the shorter wavelengths. So by picking this, we get away a lot from the interference of thermal radiation. Now here I show how the emission bands decay, comparing the spectra as they decay for two temperatures. As they decay, we excite it with a laser pulse, not a continuous, and then we watch how the emission band decays after the excitation pulse is turned off. At both 378 degrees C and 1072 degrees C, where intensity is plotted on a logarithmic scale, we see pretty straight lines. Plotted on a logarithmic scale, a straight line means you're close to a single exponential decay. You can also see that at each temperature, the lines are parallel. That means you're having a uniform decay rate all across that spectrum. So you can pick any portion of the spectrum. Here's the broadband, and at the lower temperature, you can still see some of the sharper R line, but because of the equilibrium between the states, they all give you the same decay rate, so you can pick any part. Again, when you have going to high temperatures, we pick just this part shaded in red, even though it's not at the maximum, so that we can stay away from the strong background. If you didn't have that strong background, not trying to get to super high temperatures, then you could collect much more of the emission. Then at each temperature, you can determine the decay time and plot it versus temperature. And those are the points here. You can fit it to the equation I showed you in the previous slide. Shows a nice fit. And it shows two ranges of temperature sensitivity. First, the range from about 200 to 800 degrees C, where it shows more modest temperature sensitivity, not too steep a slope. And then for temperatures above 800 degrees C, you have more temperature sensitivity, as you can see by the steeper slope here. Now I'd like to go over several applications that can be implemented with this approach. The first one being the most simple. This will be an implementation of a luminescence lifetime-based fiber optic thermometer that can be used to probe a hot gas temperature. The thermometer itself consists of a YAG optical fiber with a chrome gadolinium aluminate phosphor tip. Through the optical fiber, we can both deliver the excitation light and also collect the emission light. We can do that by using a bifurcated fiber assembly, where through one leg we can deliver the excitation, the pulsed 532 nanometer laser, and the other leg, through the other leg, we can we can transmit the collected emission through some filtering to a photomultiplier tube, where connected to an oscilloscope, we can watch how the intensity of the emission decays once that excitation pulse has ended. Here's just a photograph. This is one of the larger fibers. I picked the larger one because it takes a better picture. You can see the green 532 nanometer laser light going through it. The sensing end is inside that furnace. Okay, we can then look at we can collect our decay measurements at different furnace temperatures. And here you can see it's pretty sensitive to temperature. For some rather modest increases in temperature, we get a significant change in slope. Again, remember, the intensity is plotted on a log scale. Okay, so then at the different furnace temperatures, we can plot the decay time versus temperature, get an excellent calibration curve fit by the same equation I showed before. A very good signal to noise. And you can see this, again, this thermometer with this material is best for temperatures above 800 degrees C. That's where it has its best sensitivity. Again, I would add, if you're looking for lower temperatures, you might pull back and say go from gadolinium aluminate to yttrium aluminate, where the highly temperature sensitive range is at somewhat lower temperatures. The next two applications, we'll be looking at our chromium gadolinium aluminate as a coating for temperature sensing. In this case, as a spot temperature measurement. In particular here, for a spot on a turbine vane in an afterburner flame. Here we're looking at the temperature of the spot on. It's actually a pair of vanes. They're called a doublet that are in the same sub-assembly here. and you can see what we do. We put our chrome gadolinium aluminate coating on the top, 25 microns thick. That's deposited. We have that deposited at Penn State by Doug Wolf using electron beam physical vapor deposition. And that coating gives the coloration you see on the vein surfaces here. It's on top of an yttria stabilized zirconia thermal barrier coating, which is typically on that the component to begin with. That's for thermal protection. And so that's white. So this would look white if we didn't have this phosphor coating on top. We then mounted our vane in the back of an afterburner flame. That's a GE J85 test engine at our Arnold Engineering in Tennessee. And then I can show you, we can ramp up that afterburner throttle setting. And you'll see the flame getting stronger and stronger. And that's heating up the side of the vane that's facing the flame. If you take a photograph from the other side of the vane, you can see how that vane is glowing hot. And right here, that's the laser spot. So that's where we're collecting our temperature measurements from. Then the idea was then to measure the temperature of this spot as we throttled up that afterburner power. Okay, so here are the actual, some of the actual measurements. Here you see some of the decay curves from that emission from that spot on the vane as we change the throttle setting. This PLA is simply means a power level angle. You have a control. It's like one that would be in a cockpit where the angle of that lever goes from 90 degrees up higher, and so this is just the angle of that lever. It's that simple. And you can see how much, again, the decay gets faster and faster as you increase the temperature. You can determine the decay time is essentially related to the slopes of these plotted on logarithmically. Then to get your temperature at each setting, all we do is we determine the decay time, for example, 80 microseconds, go over to our calibration measurement, see where 80 microseconds would be about here, run over to our calibration curve, and so that with the point we meet over here, that gives us what the temperature is. In this case, 830 degrees C. If we do that for all the decays, we see that we determine the temperature at that spot range from 830 to 1027 degrees C as we change the afterburner settings. I should say that when we went out to AEDC, we also did this with some other vane doublets with different thermographic phosphors, with more conventional rare earth doped ones. And our chrome gadolinium aluminate substantially outperformed those in terms of having a much higher intensity emission and therefore better signal to noise, better temperature precision for these measurements. Now, let me go on to the last implementation, also using a temperature sensing coating. Oops. Let's go back there. Sorry about that. Just trying to get this. I think this is even more impressive, getting a whole 2D temperature sensitive map. In this case, we're using the mapping to look at cooling effectiveness as we change cooling airflows through holes well, the plan is for components, but we're starting for simplicity with test plates because the analysis of the cooling is much simpler than for holes in the actual turbine component. Now we take our plate, which again has at the top layer our chromium-doped gadolinium aluminate. We position it at an angle with respect to our burner. The flame, you see, it impinges below the cooling holes that you can see here. And I show this picture because I just wanted to show you that even with the naked eye, you can see some effect of the air film cooling. You can see these darker stripes. That's because the air jets going up across the surface here are cooling that, and it's not as essentially is not as glowing hot underneath those jets. However, your eye isn't calibrated to tell you what the temperature is, but that's where we use the luminescence based sensing. And one of the advantages of having such a strong luminescence emission is that we don't have to raster a small laser beam across our whole surface. We can just expand that beam, even though that's a lot lower in intensity per square centimeter, but we still get enough to do our mapping, and so you can expand it to an area like that, and so we'll get a map over that full area. Before I move, oops, I just wanted to give you just a little flavor of what this test looks like. I didn't want to speak about the noise, but when you run this and you change the cooling airflow, you can see these dark stripes where you have the cooling. They can grow and recede as you increase and decrease that flow. Now, first, I wanted to show you how you can construct a temperature map. It takes several steps of acquisition and image processing. The first step is a acquisition stage where you have to acquire an image stack of exposures where each exposure has an incremental increase in the delay after the laser pulse. Well, that laser pulse, remember, that corresponded to that broad green light you saw on the last slide that spread over the area we want to map. Now that's not only on, that's only on for about 10 nanoseconds at a time, and then we see how the luminescence emission decays as soon as it goes off. So what we do then is we fit a single exponential decay to the decay curve at each pixel in the stack. You can imagine if you go to one pixel in that stack, every exposure essentially covers a different part of the decay curve. So that gives us our decay curve. We can fit that to a single exponential. We do have to pick a window to span the range of the delay times after the laser pulse we want. Have to do it in an unbiased way. We developed a MATLAB routine to do that. Actually, it's Adam Wroblewski at NASA Glenn who's done that, and automatically determines those, does the window selection and then does the fitting. So at each pixel, we start with a stack, and then we come up with a decay time value for every pixel in the stack. That's what you see over here. And you can see, if you look under one of the air jets where the decay time is substantially longer than in the uncooled region. Its decay times, you can see, are substantially shorter where it's uncooled. And I've showed you a couple of graphs already that show that the decay is faster as you increase the temperature. Well, I find decay times interesting, but the end user maybe not so much. They're interested in the temperatures. So we have to convert each decay time in our map to a temperature. That's where we go back to this relationship here, where we have the relationship between tau, our temperature, the temperature decay time with capital T, the temperature, and our furnace, fitting the furnace calibrations give us all the other coefficients. Using that, then we can convert our decay time to temperature. So now we have the useful temperatures. You can see where uncooled regions are at about 900 degrees C. Cooled regions are 100 degrees C or so cooler. You can look at, get a better idea of the resolution by looking at a line scan across the surface where you have these cooling jets. Here you can see the coolest part here is about over 100 degrees C cooler than the uncooled region. But if you look at the signal to noise in here, I would maintain that we can see temperature differences probably on the order of 5 degrees C over distances less than a millimeter. Now, a very important product of our analysis is we also generate a 95% confidence map, so that's paired with each temperature map. So this map generally contains all the error bars for the temperature readings here. So if you go into one of the cooled area here, you see the confidence intervals about 5 degrees C and plus or minus 2.5 degrees C. So that's a pretty good temperature precision. Now let's go on to some temperature maps that have some interpretive value. These are temperature maps obtained as we increase the cooling air flow through these cooling holes. This M here is a measure of cooling hole. It's a dimensionless parameter that's commonly used. And as we increase that flow, I should say in the burner, the mainstream gas temperature is 1390 C. So we increase the flow, you can see the extent of the air jet cooling becomes greater, especially in length. It covers a longer and longer distance, a little bit bigger area. But very interestingly, as we continue to increase the cooling airflow, the cooling becomes much less distinct. You actually lose cooling effectiveness as you keep going up in the flow, cooling air flow. And that's due to a well-known phenomenon that air jets coming out of these holes, if it gets too fast, those jets will lift off the surface and no longer effectively cool the surface. Another interesting feature that I hope you can see there are some bright streaks to the sides of the the cooled streaks here. So it's actually hotter at these sides than it is in the uncooled regions. You can see that a little bit better looking at a line scan across the streaks. You definitely see the cooling streaks, but to each side you see it actually increases in temperature. Here about 20 degrees C hotter than the uncooled region. This is something undesirable, and this is known that this can happen because when you have an air jet that can produce vortices at its sides, and this can push down hot gas against the surface. So this is important to know, so you can pick cooling conditions that don't produce these hot streaks. Now, it turns out you can look at the effect of the cooling more clearly if you, instead of looking at the temperature maps, you can use to determine what's a parameter called AIDA, cooling effectiveness. What that does is it kind of takes the absolute values of the temperatures out of it, so you can more fairly compare across different temperature regimes. What this does is, what this shows you, I believe, more clearly is that as you increase the cooling air flow, you can see the cooling effectiveness. It becomes brighter, meaning that the magnitude of the cooling effectiveness is getting greater, as well as its spatial extent. But then again, you come to a point where as you continue to increase the cooling flow, you get less and less well-defined cooling effectiveness, less effective, and you can hardly see it at the highest airflow because the jet is lifted too far off the surface. Interestingly, though, as you continue to increase the airflow, there's another type of cooling that continues to become more and more effective, and that's in the vicinity of the cooling holes. And this is due to what I call in-hole convective cooling. That is, the cooling air cools the sides of the holes, and then when you cool the sides of the holes by conduction, it cools the area in the vicinity of those holes. And that becomes more effective even though the jets coming out are lost their effect for cooling. But this is all very important in trying to pick conditions for cooling, as well as determining the best geometry for cooling holes and the array of cooling configuration cooling hole arrays. Let me now summarize the technology benefits using this approach. First of all, it is its high temperature capability, and that because of its high intensity of the emission, that allows you to perform non-contact temperature sensing up to 1300 degrees C using the broadband luminescence emission from chromium-gadolinium aluminate and other chromium-doped illuminates. These measurements are robust. They're ideal for harsh industrial applications with significant background thermal radiation. They're durable. The measurements are immune to electromagnetic interference and chemical thermal degradation. I've shown the versatility of the applications, where I've shown implementations as a hot gas temperature probe. Can also be used as a temperature sensing coating, where you can perform either surface spot temperature measurements or 2D surface temperature mapping. I'd like to close by making sure you're aware that this technology is available for tech transfer through NASA licensing. And here I just want to give you the title of the patent that the technology is based upon. This also gives me an opportunity to give a shout out and the credit to my co-author, Matt Chambers. With that, I'd like to turn it over to Aaron and hopefully come back a little later to answer any questions you might have.